Okay, in this video I'm going to show you problem 7 and maybe problem 8 also from the homework. It says to calculate the magnitude and phase of 4 constellation points in the first quadrant. Here I drew out a 16 QAM, so we're talking about 16 QAM here, and I drew out the 16 constellation points, and they're evenly spaced in a nice evenly spaced square, 4 by 4. And the whole thing is centered on the origin. The easiest thing to do is to just go ahead and put these points at 1 and 3 in x and y. So we have the following 4 points: 1, 1, 1, 3, 3, 1, and 3, 3. The angles are easy to calculate. The arctangent of 1/3 and 1 and 3 are 18.4, 45, and 71.6 degrees. And I've labeled them 1, 2, 3, 4. Like that. And now I'm going to calculate the magnitudes, and they're straightforward also: root of 10, root of 2, root of 18, and then root of 10 again for number 4. And if I take the average of those values, I'm going to get 3. And the problem says to please take the magnitudes such that their average is 1. So I'm going to go ahead and take this 3 and divide all of the 4 previous magnitudes by 3 and get 1.054, 0.471, 1.414, and 1.054. So these average to 1, and there we've normalized the length scale so that this constellation gives us these angles and these magnitudes for constellation points 1 through 4. And it only asks for the first quadrant. Okay, so that's why we're stopping here. Let me move on to number 8. Here we have a BFSK system, and our maximum acceptable bit error rate is 10 to the minus 6. The SNR is 10 dB, which is 10 as a ratio. What we're going to do for part A is calculate the spectral efficiency required to get this bit error rate. And what we're going to do is we're going to look up on the waterfall plot in the text the value 10 to the minus 6 on the vertical and read off. It's about 13, somewhere in between 13 and 14. I'm going to call it 13.6 dB for the energy per bit divided by thermal noise density, EB over N naught. And 13.6 dB translates into 22.9 as a normal value. And it's important that you do that transformation because here we're going to deal with that value as a multiplicative thing. Okay, so we have EB over N naught times R over W is the signal to noise ratio. Why is that? Because the energy per bit times the bit rate gives the energy per second, or the energy rate, or the power, signal power. N naught times W is thermal noise density times bandwidth, which is thermal noise. So signal in the numerator, noise in the denominator. Solving for R over W, which happens to be spectral efficiency, bits per second per hertz of bandwidth used, we're going to get 0.436 for the spectral efficiency. In part B, it asks, can this spectral efficiency be achieved using raised cosine filtering with beta equals 0.5? Well, in the textbook, beta is notated as R. And for BFSK, we've got M equals 2. And so we go to equation 610 in the book, which is for MFSK, and we get that the bandwidth is equal to 1 plus R times M over log 2 of M. And M is 2 here for BFSK. Therefore, R over W, which is the data rate divided by the bandwidth, and bandwidth is called BT over here, up above, is simply log 2 of M over 1 plus R quantity times M. Plug into that and you get 1/3. And 1/3 is in fact less than the 0.436 that we require above. And so in order to get this bit error rate with this SNR, we'll have to use a different type of modulation. Okay, I'm going to stop